So we are very happy to have Boris Pioline from Paris, counting Calabi-Yau black holes with modular forms. Please.
Thank you very much. It's very nice to be back in Korea after many years. Thank you also for scheduling my talk right after Samir's, since you already introduced a number of notions that will be useful. So this talk will be based on, so it's part of a long-standing research project, which I've been doing with many people, but especially with Sergei Alexandrov and Jan Manschot, which is to try to understand to some degree of precision the counting of BPS black holes in vacua with 8 supercharges in 4 dimensions, so type 2 strings on Calabi-Yaus. And those are the main references. And so this work is already a few years old, but I would like to also cover the more recent work with Sergei, Albrecht Klem, Torsten Szymanek, a postdoc in Paris, and Soela Fezbak, who's a mathematician at the Imperial College. Okay, so let me start with some general motivation. So as we know very well, the driving force in high energy theory has been the quest for a microscopic explanation of the Wittgenstein working entropy of black holes. And string theory does provide a quantitative answer to this question in the case of BPS black holes in vacua with extended supersymmetry. Namely, at weak string coupling, these black hole microstates arise as some bound states of D branes. Sometimes we have to add along F strings, fundamental strings, or the Virtualized 5 branes. And they can sometimes, again, be counted efficiently and compared to the microscopic prediction. So on top of confirming the consistency of string theory as a theory of quantum gravity, one of the very interesting aspects is that it has opened up many fruitful connections with mathematics. And in fact, so the dialogue goes both ways. We can predict some very non-trivial features of topological invariance of Calabi-Yau threefolds using physical reasoning. And we can also talk to mathematicians and learn from them some properties that we can actually use to compute new invariants. So the context I will be talking about is that of type 2 strings compactified on the Calabi-Yau threefold, compact one. And in that context, there is a very precise mathematical description of the category of BPS states. Is the so-called derived category of covariant sheaves, which is some subtype version of vector bundles on the Calabi-Yau threefold, which you should think of them as the gauge bundle living on D6 branes. I'll talk more about this later in the talk, but the basic point is that these BPS states will be stable objects in this category, labeled by their electromagnetic charge, which is just the Chern character of the sheaf. So the rank of the sheaf is the D6 brane charge. The first Chern class Chern character will be the D4 brane charge, the D2 and D0 brane charge. Not only this category is very well defined mathematically, but also the notion of counting is precise mathematically. So in enumerative geometry, it's this index that we're trying to count the number of semi-stable objects is known as the Donaldson-Thomas invariant. It's a function of the charge vector gamma, which are the electromagnetic charges, but also of some stability condition Z, which is some extension of the notion of Kähler moduli in string theory. And so the properties of this DT invariance in general are well understood, although it's a very hard problem to compute them in explicitly for general charges. But the question is, can you compute them explicitly, determine their growth as the charge goes to infinity, and compare to the macroscopic prediction? So physical arguments predict that suitable generating series of these BPS invariants, namely those which count D4, D2, D0 bound states, should have specific modular properties. And well, the basic physical insight is that these D4, D2, D0 bound states correspond to some M5 brane wrapped on the divisor on some 4 cycle inside the Calabi-Yau. So they really describes some black strings in 5 dimensions in M-theory on Calabi-Yau. And as you reduce the black strings on the circle to 4, you get your actual BPS black holes. But in insight, the black string supports a superconformal field theory, and the elliptic genus of that superconformal field theory has to be encodes these DT invariants and has to have the usual modularity properties. So this gives a very good control on the asymptotic growth of these indices and allows to check quantitatively the exponential growth, the agreement with the macroscopic prediction. So this story has been very well developed for the simplest of all Calabi-Yau threefolds, namely torus T6, as well as K3 cross T2, and the goal is to carry the same analysis for a general compact Calabi-Yau 3. Let me just remind you of some simple, some early results in this direction in the simplest case of flat torus. So in that case, this BPS index is actually independent of the choice of moduli for the T6 or the choice of stability condition. And it only depends on a certain quartic polynomial in the charges gamma, such that the actual number for a fixed gamma will be the Fourier coefficient of some weak modular form for Fourier mode n, which is equal to this quartic invariant. So this can again be argued by understanding the word volume theory of the Defoe branes on T6, and was obtained early on by Moore, Maldacena, Strominger in the physics literature, but also recovered more recently by actual counting of stable sheaves in mathematics. And in both cases, one have this Stirling series, which has modular properties. And this gives, as I mentioned already, the easy handle on the growth of the Fourier coefficients. Just to recall some very known facts, if you have a modular form which is invariant under SL2Z, or maybe some finite index, some subgroup of SL2Z, and so it satisfies this, of course, this invariance condition with weight W, and if that form is weakly modular, namely has poles at Q goes to 0, such that the leading power minus delta here will be negative, then the Fourier coefficients will grow exponentially in a way specified by the leading exponential of 4 pi square root of delta n being the Fourier mode. This is the formula which also is known as the Caddy formula in physics, but is a general consequence of modularity invariance. And indeed, in this case, allows to reproduce the macroscopic prediction. But the story for general Calabi-Yau 3 is much more involved and interesting. So these BPS indices will all depend on the Kähler parameter, which I denote by Z here. More generally, as I'll explain, on the choice of stability condition with a complicated chamber structure. And so it doesn't really make sense to consider this Jeloning series until you specify in which chamber you evaluate each invariant. And so there's natural choice of chamber, which is the so-called attractor chamber, which is specified by the charge vector, as Samir reviewed for us in the previous talk. And so you can argue that and demonstrate in specific cases that these Jeloning series are no longer modular, as predicted naively from the idea of the underlying conformal field theory, but rather modular. What this means is that their transformation on the SL2Z is not just the usual rescaling by a power of theta plus d, but involves some anomalous inhomogeneous piece, which in the simplest form can be, arises in this way. So this is one possible way of deforming the transformations of a function of tau under SL2Z such that it preserves the group action. And this deformation is governed by some underlying ordinary modular form G, which is called the shadow of the Mach modular form. And so it's some rather complicated transformation property, but for this holomorphic generating series, but which you can rewrite as an ordinary transformation property for the so-called non-holomorphic completion. So starting from the original holomorphic function of tau, Q series, you can add to it some non-holomorphic term. So it's non-holomorphic because it's an integral from minus tau bar to I infinity, such that the sum of the two pieces has the ordinary transformation properties, but the object is no longer holomorphic. So this is only the simplest example of the kind of quasi-modular generating series which appear when you consider GT invariance on a general Calabi-Yau 3. In the case of x equals K3 equals T2, as demonstrated by Dabholkar, Murthy, and Zagier already more than 10 years ago, the kind of generating series that arise are exactly of this type, where the shadow is governed by the counting of half BPS dions, from which you can build quarter BPS black holes, which are the objects that you are counting. So, so this lack of this breaking or anomalous transformation under modularity is a consequence of Wall crossing, and takes a simple form, or rather simple form, in cases with half maximal supersymmetry, such as n equal to 4 supersymmetry, such as type 2 and K3 cross T2, where the only bound states that can contribute are these two sentence bound states. But for general Calabi-Yau 3, you have to deal with arbitrary number of centers, and as a result, you have to generalize this story drastically. So, which is what I just wrote here. So we have in the previous work, which I will review next few slides, with Sergei and Jan, we have actually determined what are the precise modularity constraints on this generating series of D4, D2, D0 invariants. And so the goal in this talk will be to exploit these properties to actually determine these indices in some explicit examples of Calabi-Yau threefolds, such as the quintic in P4 and other one-parameter models, where we have still some control on the chamber structure, such that we can determine explicitly some of these indices and check or give some checks on the modular predictions. So this is actually this is not this kind of story was looked at already a long time ago by Gayotto, Strominger, and Yin in 2006, and many subsequent works. But so at the time, people did not quite understand all the details of these Wall crossing properties and the ensuing lack of modularity. So our goal is to revisit this analysis using some new technology which has become available in the mathematics literature in several works by Suella Feisbach, who's a collaborator on this recent paper, and Richard Thomas, which gives some very interesting relations between these D4, D2, D0 indices, which in general are very hard to compute, and some invariants which are more so-called Gopakumov-alpha invariants, for which we have some leverage on. And so there's what I will explain is some interesting interplay between the story of black hole counting and the story of enumerative geometry and topological strings on Calabi-Yau threefold. So the outline is as follows. I'll review some mathematical background on this Bridgeland stability conditions, which really play an important role in giving us methods to compute this invariance. I will then review the previous work with on the modular general predictions of modular predictions for this generating series of rank 0 DT invariants. So rank 0 here means that the D6 branch charge is equal to 0. So the D4, D2, D0 indices. And then I'll discuss, present some tests of this on this compact Calabi-Yau threefolds with one modulus, which is the case which is currently accessible using these new mathematical methods. So yes, please help me with asking questions. Yeah, so those relations come from studying row crossing, not quite in the physical space of Keller model, physical Keller model space, but in this enlarged space of Bridgeland stability conditions. And so it's so this is essentially the main results of Feisbach and Thomas. That's the first relation between these D4, D2, D0s and the D6, D2, D0s. And then you have to invoke the standard relation between this rank 1 D6 and Gopakumab alpha invariance, which goes back to Molik, Nekrasov, Pandari Pandey, and MNOP. Okunkov, thank you. Okay. Thank you. Okay, so let me start with just some mathematical preliminaries about this category of BPS states in type 2A, which is the bounded derived categories of current sheaves. So, as I said, the current sheaf is a generalization of a vector bundle where the rank of the bundle might jump on some complex codimension 1 or higher loci, corresponding to D4 brane or D2 branes D branes with lower dimensional support. But that's not really enough. You need to consider the complexes of such current sheaves with maps corresponding to open strings between each of these objects. And so each of these objects sits at a particular place in the complex, labeled by an integer k. You can think of the objects at even position as D branes. Those at odd positions are as anti-D branes. The total charge carried by such a complex is just the sum of the Chen classes for each of the sheaves, weighted by a sign -1 to the k. Hence the fact that the D brane goes to anti-D brane if you shift the complex by 1 unit. And so on this, so between any two objects, you can consider the number of straight open strings, which provides a antisymmetric pairing between the charges of the object, which in physics would just be the Dirac, Schwinger, Zwanziger pairing, just given by some simple integral of characteristic classes on the product of Chen vectors on the threefold. So that's the category of BPS states, out of which you have to select the stable objects. So for this, you need a notion of stability condition. So that's so in mathematical terms, it's a pair of a holomorphic, of a linear map Z from the charge lattice to the C numbers. So in physics, this would just be the central charge function, as well as some abelian subcategory A of the total category C, which satisfies a number of axioms. It's called a heart of bounded T structure. I don't want to go into the details of it, but just mention that one of the conditions is that the imaginary part of all the objects inside this subcategory A should be positive. So A is kind of choosing a subset of BPS states out of which you can construct all possible bound states, whereas A shifted by 1 would correspond to the anti-BPS states. So, but the point is that locally, so it's hard in general to construct these stability conditions, but locally, at least, if you know at one point this heart for given Z, if you slightly deform the central charge, you know how to deform this heart A. So the dimension of the space of stability conditions is just the dimension of the space of linear forms from the lattice to C. In other words, it's the rank of the charge lattice, which is just the sum of even Bethe numbers of the Calabi-Yau 3. So that's actually quite bigger, almost twice bigger as the usual Kähler moduli space, which would just be B2 of X. But this is the largest space in which you can define the notion of Donaldson-Thomas theory. This is a natural setup for defining the Donaldson-Thomas invariance. And as I will try to convince you, it's actually very useful to exploit this larger space to make, even if you're interested in computing the indices along the physical slice. So it's generally hard to construct, to show even the existence of such stability conditions, even though it's of course very much expected. But the kind of still the state of the art is a paper from a few years ago by Chuni Lee on constructing this on the quintic, and then there are a handful more cases. But we'll assume that such stability condition exists, and in fact their construction is automatic once you assume you have some certain inequality on the Chen classes of so-called tilt-stable objects, which allow you to construct some weak stability conditions. And those will be the ones that we actually require to perform this analysis. So I'll come back to this inequality because it has some interesting physics interpretation as well. But so eventually we're interested in computing these indices along the so-called physical slice, which is given by central charge functions, which are not arbitrary functions of the charges, but which come from some prepotential, or if you like, are given from by mirror symmetry as the period integral of the polymorphic 3 form on the dual 3 cycle corresponding to gamma. In other words, you cannot choose independently the central charges for the electric and magnetic components. They are related, such a way that the total dimension the allowed dimensional space of the stability conditions that you can probe in string theory is B2 of X, well, plus 1 because of some trivial rescaling, or B3 of the mirror of X. If you're just interested in working at large volume, there is an explicit formula for the central charge of any coherent sheaf, just coming from essentially the volume of, well, the integral of the Chen character times the exponential of the Kähler form, which essentially computes the volume of the D6 brane, or the action of the D6 brane attached to a given bound coherent sheaf E. Okay, so having these stability conditions, we can define the notion of semi-stable objects. Probably I don't want to go into this mathematical detail, but those would be objects which such that all sub-objects have a central charge with a phase which is less than the one of the original object. Then you can look at the moduli space of such semi-stable objects. It's in general a rather complicated scheme or moduli stack, and there is a lot of work to even define what the DT invariant is. What you can define using this method in Nelson-Thomas theory is some rational valued quantity, which is related to the physical BPS index in general by a multi-cover formula. So if you start from this rational indices omega bar of sigma, and you process through this sum over divisors, where mu here is the Möbius function, the conjecture, mathematical conjecture, is that the result of it is an integer and coincides with the physical BPS index. But mathematicians, prefer to work with these rational indices, which are much easier, to define, and have this simpler word crossing properties. So some examples of this are, if you consider a sheaf which is supported on k points, so which has a vanishing rank, vanishing C1, C2, but has CH3 equals to k, then the moduli space of such sheaves will just be the Calabi-Yau itself, and so therefore this DT invariant will be the Euler number of the Calabi-Yau for arbitrary value of k. This is a completely universal result. If you start looking for BPS indices counting D2, D0 brane, so some D2 brane charge beta in second homology plus k times the point charge, so k units of D0 brane, then you can also show that this invariant here is actually equal to the Gopakumar-Vafa invariant of degree beta at genus 0. So Gopakumar-Vafa invariants count D2, D0 bound states. But then the question, so then for modular charges is in general a complicated story. And those are, I should mention, the result in the large volume limit. Now let me say a few words about word crossing. So these indices are, because they are they are locally constant on this space of stability conditions, but they will jump across some walls of measure stability, where the central charge Z of gamma aligns with the central charge of sub-object gamma prime. So those are some real codimensional walls with across which the jump is completely determined in terms of the indices on one side by the formulas which first appeared in the math literature by Joyce Song and Consavi-Zauberman. There is a very clear physical understanding of these jumps in terms of appearance or disappearance or multi-centered black hole bound states, such that the simplest example being a case where you, on one side of the wall, you just have an object of charge gamma 1 plus gamma 2, which exists, whereas on the other side, you have the same object plus a bound state of charge gamma 1 and gamma 2, which carries an index given by the product of the indices times some angular momentum factor coming from the relative dynamics. Okay, so there's still one piece of information that we know already for arbitrary Calabi-Yau threefold, which is this relation between Gopakumar-Vafa invariants and counting of D6 branes with a single unit of D6 brane charge. So this is what I was mentioning earlier in answering a serious question, relation due to Molik, Nekrasov, Okunkov, and Aripande, which states that for 1 unit of D6 brane charge, but arbitrary D2 and D0 brane charge, you can obtain these DT invariants at large volume from the knowledge of the Gopakumar-Vafa invariants at arbitrary genus by such a formula. In fact, both sides of this equal sign up to some powers of this Magdaon function here can be interpreted or are equal to the topological string partition function. for certain identifications of the Kähler modulus Z and the topological string coupling lambda with the variable Q, which is conjugate to the D0 brane charge, and V, which is conjugate to the D2 brane charge. So this is one source of information that we can exploit. This topological string amplitude has been computed methods have been developed to compute it to high genus using the so-called integration method, using the holomorphic anomaly equation satisfied by the topological string amplitudes. And so we have knowledge of this, both of the D2, D0 indices as well as the D6, D2, D0 at large volume. And so that will be the basis for making this, the starting point for computing the D4, D2, D0 at, in the large volume region as well. And so this is the main mathematical tool that we're going to use. This results by Feisbach and Thomas over a series of papers, which essentially show that for any Calabi-Yau, polarized Calabi-Yau threefold, so polarization means that you choose one particular direction in the Kähler cone, then so the rank R dt invariance, counting bound states of R D6 branes with any rank R, could even be 0, are in fact determined by the rank 1 dt invariance, and therefore by the Gopakumar-Vafa invariance using this MNOP relation. An interpretation of what? Yeah, so I'm explaining so the theorem follows by wall crossing, but it's wall crossing in a non-physical slice of stability conditions. So how should I say? So you can try to reinterpret the result of these relations in physical terms, and it's only possible in some simple cases. So this relation is shown in complete generality, but is usually not explicit, and it's only for simple cases that you can actually make it explicit, and then try to identify it. The contributions in terms of physical bound states.
So now I believe my understanding is that this rank R DT invariance come from 6-dimensional UR gauge theory. So that sounds like the UR gauge theory is completely determined by U1.
Yeah, that's true. That's the statement, and it's a very non-trivial statement at the physical level. I mean, yeah, once again, it follows from wall crossing, and there's no simple formula that expresses the result. So it's hard to even prove it physically. In general, so I'll be explaining cases where there are explicit formulas, and I don't know how to interpret them in terms of this gauge theory in 6 dimensions. In fact, I'll be interested in the rank 0 case where if at all, there should be a relation to a gauge theory on the divisor on the 4th cycle rather than on the 6th cycle. Now I'm only with time. Okay. So I think the idea is interesting. So these authors rely on wall crossing not in physical stability condition space, but in some boundary of it, which uses the so-called weak stability conditions. And this is, they are determined by a central charge function, which is very close to being the large central charge function for D branes on the Calabi-Yau threefold, which in general would be the volume of the Calabi-Yau 3 times the rank, plus the volume of the divisor times the CH1, etc. So the key is to set by hand to 0 the contribution of the D0 branes. So that's now That's a rather severe modification from the physics point of view, but you would expect that at large volume, these contributions don't play a role. So it's as a first, actually a natural first step in constructing full-fledged stability conditions at large volume. And well, the good thing about this slice is that the shape or the form of the chamber structure is very simple. The form of the walls is very simple, and so you can actually get some control on the chamber structure. But this and moreover, there is a constraint on the existence of a semi-stable object for this particular simple family of stability conditions, which enters as a key step in constructing actual boundary stability conditions from those. Now, this conjecture is that there will only exist semi-stable objects if the Chern classes of your object E satisfy such a linear inequality in terms of the B field, B, as well as the Kähler modulus T. So B and T parameterize the B field and essentially the volume of the Calabi-Yau threefold in this direction chosen by H. So this is the so-called Bayer-Macri-Toda inequality. It's in general conjectural, but shown, as I mentioned, for the quintic and several other simple cases. And so if this inequality is violated, it means that there is an empty chamber, and that gives you a starting point for computing the indices in other chambers. So, as I mentioned, in this space, the walls are extremely simple because the central charge is polynomial. The walls are just half circles, in fact, nested half circles in the Poincaré upper half plane labeled by B and T. And this B and T inequality, in favorable cases, defines some region inside this wall, inside this upper half plane, where the index vanishes. And so you can compute it elsewhere by sequence of wall crossing. Let me just, so in general, we don't really understand the physics of it, but we do understand one aspect of it, which is that this inequality will leave an empty chamber, so we'll define an empty region above this above the real axis if it crosses the axis, basically. So you require that the discriminants of this quantity with respect to B at t equals 0 should be positive, and that gives a quartic condition on the Chern classes, which in fact you recognize as being the quartic invariant that controls the entropy of single-centered black holes. So what you see is that there will exist an empty chamber if the if the quartic invariant for the corresponding charges is negative, which means that there is no single-centered black hole with the corresponding charges. So either you have a single-centered black hole or you have an empty chamber, and that makes some physical sense because we expect that if there is a single-centered black hole, it will never decay and it won't be able to find a chamber where the index is 0. Okay, so that's, yes. This is the case which I will consider. So B2 equals to 1. The theorem is modular. It applies in any one-dimensional direction in Kähler moduli space. Yes. Yeah, and you have to assume or to prove this inequality in all directions before you can construct the Brillouin stability conditions. Alrighty. So now let's go. Let's go back to this modularity constraints on D4, D2, D0 invariance. So as I mentioned before, based on this idea of the D4, D2, D0 coming from wrapped M5 branes on the divisor. One generally expects that the generating series of these indices, so 0 unit of D4 and then some fixed D4 brane charge, as well as fixed D2 brane charge, and some other arbitrary units of D0 with some power of Q to the N. You can just forget the decoration here. Should correspond to the elliptic genus of this 5 brane after you sum over the D2 brane as well. And so in general, it should be a vector valued weakly holomorphic modular form with a certain fixed weight prescribed by the dimension of the lattice of charges on the D4 brane, and prescribed multiplier system. So this property is expected, but you can using various arguments that we developed over the years with Sergei and Jan, trying to understand the geometry of hypermultiplate moduli spaces, we could come up with a more precise characterization of the properties of this series. So first of all, the chamber in which you should evaluate this DT invariance is specified to be the large volume attractor chamber. So you have to compute them in a particular direction in the Kähler cone fixed by the magnetic as well as the electric charges. So this matrix kappa AB here is kappa upper AB is the inverse of the matrix kappa lower AB, which is given by intersection between with the divisor with charge P with a D4 brane divisor. Okay. Now so what does vector valued weakly model means? So in principle, we have an infinite family of such generating series labeled by the D2 brane charge QA, but in fact, there is only a finite number of them because of a so-called spectral flow symmetry. We can shift the D2 brane charge by some integer or by some lattice vector rather, by tensoring the current shift with the M units with a line bundle with the M units of flux. This also shifts the D0 brane charge. But at any rate, you see that so you can get rid of most of the D2 brane charge except for some coset in the discriminant group lambda star over lambda, where lambda is I think the lattice of D4 brane charges and lambda star the lattice of D2 brane charges. So this gives rise, so we just have a finite number of possible values for this D2 brane charge, and the fact that it transforms as vector valued means that under tau goes to -1 over tau, for fixed D4 brane charge, the vector labeled by D2 brane charges gets mixed up to essentially by some discrete Fourier transform. So in other words, it transforms in the Weil representation of the metaplectic cover of SL2Z. And yeah, so as I mentioned, if you take the product between this vector valued holomorphic form and certain theta series, you restore the sum over all D2 brane charges, and in this way, you recover what should be the 5 brane elliptic genus. Now this is actually only so the true when the divisor, so the D4 brane charge is irreducible. If it's not, then we have this possibility of the D4 brane charge splitting into various subpieces. So the state to decay into bound states of D4 brane charge with lower D4 brane charge, and as a result, we could show that this vector valued object is no longer modular but mock modular in a very precise sense. So there exists so for any fixed P, which is the sum, so you have to look at all possible decompositions of P into sums of Pi, where this takes values in lattice of effective divisors, so positive d4 branch charges. And and there exists some explicit theta series such that if you multiply them with the product of the contribution from each constituents, then the total thing is no longer holomorphic, but it is modular, just in the way that was predicted by, has the same modular properties as if the divisor was irreducible. So this object is mod modular. Those objects will have their own mod modular property, but as you take these combinations, you get ordinary modular objects which are non-holomorphic, but whose holomorphic anomaly is recursively determined in terms of the anomalies of the subobjects.
Is there a simple explanation of why these are modular or not modular?
So physically, we expect the non-holomorphic terms in the elliptic genus. If you think in terms of elliptic genus on this fibrane wrapped on the reducible divisors, we expect them to come from the contribution of non-compact directions due to possibility of separating the various divisors. But this is not really, I don't understand well enough the theory of multiple M5 branes to be able to predict it using this reasoning. So the way we arrive at this is by a rather orthogonal line of argument relating them to instanton corrections on moduli spaces, which then we know we have much more knowledge about. But the physics of it it should come from contributions of marginal bound states due to unbound constituents. So the modular property, at the heart is coming from just the wordsheet duality of the M5 brane wrapped on the divisor times T2, right? Yeah. So we're counting states in 4 dimensions coming from M5 brane on the 4 cycle times a circle. But to make a quadration function, there's an extra thermal circle, and the whole thing makes a T2, out of which you get the SL2Z, right?
This is a speculative. Is it possible to modular?
So, well, I'm not sure what you mean by modular bootstrap. It's in the title of one of the papers that I'm trying to cover. So it will be modular bootstrap in the sense that, assuming these modularity properties, we will try to compute the first few terms in the Q expansion, and from it bootstrap the whole thing to find a unique series which reproduces all of them. Yeah, that's the idea. So you can call it mock modular bootstrap if you want to make it more sexy, and that's what I hope to be able to do within the next 15 minutes, I guess. So yeah, so there are some very precise prescription how to construct this theta series. For lack of time, I will skip this. And now turn to actual examples, namely try to exploit these mock modularity constraints to determine these D4, D2, D0s for simple compact Calabi-Yau threefolds, such as with 1 Kähler modulus, such as the quintic, revisiting the analysis of this gentleman in 2006. And first, starting even with 1 unit of D4 brane, where the divisor is still irreducible. This was the case which was looked at that time, but now we should be able to do slightly better, and in principle, prove. Well, this early work, let me say, involved a lot of guessing, and we want to actually get more solid arguments to really check if this to really compute this series. Anyway. So yeah, so for n equals to 1, you can forget about mock modularity. This joining series should just be a vector-valued modular form of weight -3/2. Again, transforming in some k-dimensional kappa dimensional representation, where kappa is the self-intersection of the divisor H which is essentially the order of this discriminant group, so the size of the vector. So the list of the examples in which we can carry this through are this familiar one parameter Calabi-Yau threefolds, which are of hypergeometric type, starting with so they are usually hypersurfaces or product of hypersurfaces in weighted projective space. And they have been looked at much in the previous literature on mirror symmetry and topological strings and so on. So there is a list of 13 examples, I think. The self-intersection kappa is listed here. It is 5 for the quintic, so it's the size of the modular vector. And I will explain some of the data later on. So we know exactly what is the space in which this series live. And in fact, we know the dimension of it. In general, you expect the dimension to be given by the number of polar terms in this weak modular form of negative weight. But the dimension should be bounded by the number of polar terms. But in general, there would be some constraints on the coefficients, which are necessary for the existence of a weak modular form. And those constraints come from existence of cusp forms in dual weight. So the dual weight of W is 2 minus W. This will be weight 2 plus 3/2. And so you can actually compute the dimension of these spaces and see. So here's the number of polar terms, and those are the number of constraints on polar terms that need to be satisfied for existence of a modular form. So the first non-trivial case occurs here for the bicubic in P5, which is one of the. So the red are the examples that Gayotto, Strominger, Yin studied at the time. And so what you need is just an explicit basis of this space, and then you should be able to compute the first few terms in the series and see whether it matches a particular linear combination. Well, one way of constructing a basis is to start from a theta series just for the one-dimensional lattice with the quadratic form kappa k square, which is the lattice of D2 brane charges. It's vector valued because of this Q index lives in Z mod kappa Z. Yeah, I should have warned you that I'm using straight Q for e to the 2 pi I tau and curly Q, italic Q for the D2 brane charge. And this is probably not optimal, but that's what it is. So once you have this object has the right vector valued property, but not the right weight, so you can act with some further Serre derivatives, which increase the weight by 2, multiplied by Eisenstein series, and divide by suitable power of Dedekind eta function to get the desired pole at infinity. Okay, so now, so what you need to do, I think the basis is to find a reliable way of computing the first few terms in the Q expansion. So this is where this technology, mathematical technology comes in very handy. So we can we can use this general relation of Feisbach et al. To determine the number of bound states for low number of D0 brane. So you expect physically that they would come from bound states of a D6 brane and anti-D6 brane with unit D6 brane charge on both sides. So and mathematically, indeed, you can show using these arguments that this would be this D4, D2, D0 index would be a sum of all possible splittings of the total charge Q into Q1 plus Q2 of the product of the indices carried by the D6 brane, which is the DT invariant, related by MNOP to the Gopakumar-Vafa invariance, as well as the PT invariants, Pandari-Pandey-Thomas, which are small, a version closely related to the Donaldson-Thomas invariant by Wall crossing at infinity. So those guys count D6 branes, those guys count anti-D6 brane. And this product of charges is the usual angular momentum from the two-centered bound state. Well, this formula actually was already obtained more than 10 years ago by Yakunibu Toda in his mathematical proof of OSV. But the trouble is that it only works for very small D0 brane charge, and in fact only allows to set the first coefficient of this series, so it's not very, very powerful. So we need something better. And so the point is that rather than looking at wall crossing for the state that we're interested in, which is this D4, D2, D0 brane, we can look at wall crossing for something else, but which will pick contributions from D4, D2, D0 bound states itself. So this is the key idea in this work of Faceback, is the latest one, in which you consider wall crossing from an anti-D6 brane with fixed D2 and D0. And you can argue that if under certain conditions of this D2, D0, which should be large enough, then there is an empty chamber for this particular state, and then a single wall where outside the wall you have a contribution from a bound state of, so inside the bound state of a D6 bar and a D4 brane. So at infinity, the number of anti-D6 branes is 0 inside the wall plus the contribution from the bound state, which is the product of the index of the D4 brane, or D4, D2, D0, which you are interested in computing, and the number of states of the pure D6 bar, which is just equal to 1 because it's an ordinary, well, it's just the structure sheaf of the Calabi-Yau threefold with 1 unit of flux. Yeah, but the index is invariant under shifting by the flux by 1 unit. And so this, you get a different way of computing this D4, D2, D0 index by considering the ratio of this PT index at large volume, which we know, which is related also to Gopakumab alpha, and just this simple bound state contribution. All right, so well, using this idea, we could actually compute not only the first few, well, not only the polar terms in this joining series for the quintic. So for the quintic, we have five-dimensional vector, but there are some symmetries relating plus or minus 1, plus minus 2. And the underlining means refers to the polar terms, those which have a negative power of q. But we could actually compute a lot more of them using this idea and check that they fit on the nose with, so there exists a single weak modular form which produces not only the polar terms but also all these higher modes. So just on the base, so in the earlier work of Gayotto, Stroman-Jurien, they were also using some guesswork able to compute the polar terms and figure out the same result. But now we can do much more and test the modularity by going to high order in the Q expansion. Now I think I'm essentially already almost over time, so I just want to mention that in work to appear, we are generalizing this to 2 units of D4 brane charge, where Mach modularity really starts to play a role. In that case, you first have to construct a basis of your space of Mach modular forms, and then find the Q series, and find the first few terms in the expansion. Turns out, I don't have time to go through this, just to highlight the fact that to construct the basis of this, even in the compact case, at rank 2, it turns out that you can recycle what is already known on non-compact Calabi-Yaus, like local P2. So similar Mach modular anomaly appears in Vafa-Witten on P2, and turns out that the modular anomaly is the same in both cases. It involves this, even though the constituents and the total objects are different, the way you can construct the modular completion involves the same objects. So by similarly computing the first few terms in the Q series, we can determine, in fact, the full generating series. This is the simplest example involving x10 is the example where the dimension vector is the smallest possible, and so the full result turns out, yeah, we can essentially compute these Q terms here plus a couple ones and check that indeed this is the only this satisfies the this is the only element in this basis of modular objects which meets this requirement. By the way, I did not get to say it, but at rank 1, this also was an example that Gayotto, Strom, and Jolien considered. And on the basis of their guess, they had a slightly different result for 1 unit of d4 brane charge. Now we can actually compute this number rigorously so it still remains to understand. Yeah, we don't have a very good physical understanding of this even at rank 1 case of these low-lying polar terms, but we have at least some mathematical handle on them. Okay, it's good. So this was a story. So the way we reached, so the way we are able to compute this rank 0 DT invariance was by starting with Gopakumab alpha invariance, using this MNOP relation to determine the DT and PT invariance, counting D4 or anti-D4 branes with a single. And then using wall crossing, these arguments, we could achieve this. If we assume that the total result should be modular, where we can, starting from the first few that we compute, predict an infinite number of them. And so we can try now to inverse the arrows and obtain more information about Gopakumab alpha invariance. And so in this way, we can actually push up the maximal genus at which one can perform the direct integration. So using kind of ordinary constraints from the conifold, from the behavior of the topological string at large volume and at the conifold. Previously, for the quintic, one could only hope to get up to genus 53, but using this modular constraints now, predictions, we can push it higher, for example, to 69 for X5, or even using this rank 2 results up to 90, 91 for X10. So the story goes both ways, and I think it's quite promising to that. Excuse me again. Oh yes, sorry. So the last column is what we have actually been able to get on the computer. This is the available genus. So for the quintic, we have it up to 64. It's just a matter of being patient, let the computer run. So it's not a terribly efficient algorithm, but it's much improved compared to previous studies. This was until just last year, this was the theoretically obtainable genus, but in practice, people were not able to go as far. Anyway, so we need to have this high genus information to put into this wall crossing arguments, and so we have to play on both boards at the same time. Okay, so just to quickly summarize, I hope I convinced you that wall crossing in the full space of instability conditions is a powerful tool for computing BPS indices, even though the physical interpretation away from the pi stability slice is a bit obscure. There is one natural deformation parameter, which is the topological string coupling itself. You might think of using the full string amplitude as opposed to the tree-level genus 0 part in the prepotential, but that's only one direction, and it's not clear even that that's mathematically sensible, or physically sensible, excuse me. Now, the other thing is that we don't really understand why these generating series should be modular. Physically, we have very good arguments, but mathematically, it's still quite mysterious. When the Calabi-R3 has a torus vibration, well, then you can in fact use Fourier-Mukai duality or T duality to argue or to show that this Jennings series will be modular, as long as the D4 branes wrap the torus. Same in K3 fibrations. If the D4 brane is wrapped on the K3, then you can actually relate this DT invariance to Nuttall-Lefschetz invariance, and those are modular by some deep results of Kudla-Milson and Borchers. But in general, we don't know, and those are examples actually which have more than 1 killer modulus. So we're currently investigating this in this example. And yeah, so if you're optimistic, you can hope that the full understanding of this mock modularity of D4, D2 indices will allow us to bootstrap not only the Jennings series, but also the topological string itself to arbitrary genus. That's for the future. So thanks for your patience.